call is now being recorded.
Hello everyone, this is Dr.S.Selvi from the Department of Information Technology, Erode Sengunthar Engineering College, Palindrome. So in this session, we are going to see about the context-free grammars. So a context-free grammar is a notation for describing the languages. So it is more powerful than the finite automata and the regular expressions, but it still cannot define some possible languages. So it is used for particularly nested structures, for example, parentheses in programming languages to check the syntax of a particular programming statements and so on. So context-free grammar can be technically defined in a form of four tuples, G equal to VTPS, whereas V is nothing but a set of variables or non-terminals. The T can be a set of terminals and it can also include the epsilon. Whereas P is a set of productions, so which has a form of V sent to alpha 1 or alpha 2 and etc. So where alpha 1, alpha 2 were on the right side of the productions, so which has a combination of terminals and non-terminals. Next, yes. So yes is the starting variable or the starting non-terminal. So the conversions, what are the conversions that are used in context-free grammar? So in terminal symbols, so it can be represented by means of lowercase alphabets, A, B, C, etc. to Z. Next, it also can include alpha, beta, gamma, and etc. Some special characters also. Similarly, it can also include dollar, comma, full stop, and so on. So non-terminals, it can be represented by means of only capital letters A, B, C and X, Y, Z and still X, Y, Z. So what is a terminal? A terminal is a symbol of the alphabet which is for which the language is being defined. Next, variables. Variables is also called as non-terminals. It is a finite set of other symbols, so which is used to represent a language. So the variables are nothing but which can be expanded in terms of terminals. Next, a starting symbol or a starting non-terminal. So this is the language. This is the variable from which the language is being defined initially. The production. So the productions, it has a form of a variable or non-terminal tends to a string of variables and non-terminals. So in the left side of the production you'll be having a non-terminal, and in the right side of the production you'll be having a combination of variables and no and terminals. So we have seen the conventions also A, B, C. So these are all variables. Small a, b, c. The small alphabets are also terminals, and capital X, Y, Z. It can be either terminals or variables, and W, X, Y, Z. So this can be only terminals. Whereas the alpha, beta, gamma, etc. So they are purely, most situations it will be a string of terminals. So, and depending upon the types of grammar, so these special characters can also be acting as a non-variable. For example, context sensitive grammar, it will be acting as a non-variables too. So the structure of the productions we see right now. So in elaborately we can see here. So the left side of the production, you'll be saying it as the head or a non-terminal, which is being expanded or which is being replaced by a set of the its body of the productions. So the body of the productions are generally in the right side of the productions, so which could be represented in the form of alpha 1, alpha 2, etc. to alpha k. So the right side of the productions can be any number of alternatives. So the left side of the production, the non-terminal, can be substituted with any one of the alternatives in the right side of the productions. So the above productions, so which are the right side of the productions which are being separated by means of mm, uh, are being separated by means of parallel symbols. So this can also be rewritten as into any number. It can be splitted into any number of productions also. So here A tends to alpha 1, alpha 2, etc. It can be written as a single production, or it can also be represented as A tends to alpha 1, A tends to alpha 2, A tends to alpha 3, and etc. to A tends to alpha k. So where these grammars can be used? So the applications of grammars. So mainly the context-free grammars are used in defining the structure of the programming languages. So it defines the structure of the programming languages, and it is used in compilers. It plays a key role in compilers, and in particular for parsing it and taking a string-based program and figuring it what it means. So mainly for the parsing techniques. And it can also be used to find out the syntactic, it defines syntactic representations of a language. So it blurs out the errors. So it analyzes the programming language right from the first line to the till the last line of any types of languages. Let us take C, Java, and anything. So it diagnoses the languages one by one, and also diagnoses the structure of the language, and it blurs out the errors, syntactical errors, if there is any. So this could be clearly identified by means of grammars. So let us go with the first example. So let us construct a context-free grammar for a language L equal to 0 power n, 1 power n. So where n can be greater than or equal to 1. So here 0 power n, 1 power n, it means so any number of zeros, n number of zeros followed by n number of ones. So it can be 0011 or single zero. N can be 1. If it is n equal to 1, it can be 01. If it is n equal to 2, it is 0011. And if it is n equal to 3, it is 00011, and so on. So these are the strings that are represented or that are included in the language 0 power n, 1 power n. Whereas if it is 00011, so it is not a string belongs to this language. So for this, the productions can be designed as. So clearly from the language, you can identify that the terminals are the zeros and ones. Whereas you can all define your own non-terminals, and you can redefine the productions based on the language which is being given. So here I am using the starting non-terminal yes. So yes equal to 0, 1. So initially for this, the basic languages, the languages that can be represented can be, so initially when n equal to 1, I also said already it can be 0, 1. If it is n equal to 2, it is 0011 and 00011 and so on. So this is the language. So here the 0, 1 is represented as a basic string of the language. So whereas after the induction, so when you're coming with induction step, so it can be when n is greater than 1. So it can be 0011, 00011, and so on. So here the base string is 0, 1. So automatically the starting non-terminal yes, so it could be substituted with 0, 1. So when n equal to 1, it could be automatically 0, 1. Whereas when you're going with this, when you're dealing with n is greater than 1, so here you can rewrite the productions. You can generate a new production as 0s1. So this is an uh, iterative replacements. So the context-free grammar, in particularly the productions. So the productions could be generated in a form of an iterative manner. So here 0s1. So for this, we can take one more example here. That is, if it is 0 power 1, if n is equal to 3. So when n equal to 3, so automatically the string can be 000 and 11. So how it can be derived? So initially the derivation starts from the starting non-terminal. So yes, automatically based upon the string what we have to generate it. So here you can either replace s by 01 or 0s1. You can choose any one of the alternative. So here I am going with, based upon the language I am in need, I'll go with 0s1. So here again, it will be again defined as. So again, this yes is a terminal which has to be again replaced. So here I can write as 0, 0, yes, 1, 1. So here the 0 is again substituted, the 0 is again substituted with 0 S1. So now what we have to do here? Again it could be, the S can be replaced with again 0. So here S can be replaced with 0, 1. So we can choose the first alternative here. So 0, 0, 0, 0, 1, 1, 1. So here, so for the first two replacement, you have used, you have replaced S with 0, S1, and for the last replacement, you have used, instead of S, you have used 0, 1. So in this manner, you can perform the derivations. So automatically, so the required string is being produced from the starting non-terminal. As a result, this string 00011 automatically belongs to the language L. Let's go with the next example. So we are going to generate a or construct a context-free grammar for the language for balanced parenthesis. So balanced parenthesis is nothing but you have to check whether the equal number of open brackets are equal to that of are same as that of, or same in number as that of the its corresponding closing brackets. So if there are two opening brackets, there should be two closing brackets. So the brackets can be a square bracket or round bracket or parenthesis and so on. So here we have chosen only the round brackets here. So here, so what could be the CFG here? So G equal to, so G is the productions. So S tends to, for this, you can also generate the language here. So automatically L equal to, initially it can be epsilon. So it can be initially epsilon. So this is a balanced parenthesis. So it should not necessarily have the parenthesis. If there is no parenthesis, then automatically it's epsilon. Next. So it can have a single parenthesis or two opening, two closed braces, or inside it you can have and so on. So these are all some examples of the open, balanced parenthesis. So for this, the productions can be written as S tends to open. So the initial base string is epsilon, so you can replace, you can choose, you can have one of the options. Next, it can also have double bracket, open bracket, yes, close bracket. So whenever there is a open bracket, there should be a close bracket. So with that assumptions, we have choose one of the alternative as open bracket, yes, close bracket. One more, it can be yeses. So that means, for example, you can also have in similar manner, open bracket, close bracket, open bracket, close bracket. So this could also be a perfect balance parenthesis. So now we can go with an example. So how we did interpret this string, that is this, using this grammar. So I'll okay here. So initially it will be a starting string. Next, so based upon the parenthesis here, so I'll go with the first alternative, yes. Okay. Next, second one. So again the S can be replaced with one more yes. So this could be okay. So here in the given string, there are 4 open braces and 4 closed braces. Okay, so based on that, I am choosing the alternatives. So here, again the S can be replaced with one more open, first option. Next, again S can be replaced with the first operation. Next, so finally you got the string, but still you're having S. So in this last derivation, you can replace S with epsilon. So when there is an epsilon, automatically you will be getting the required string here. Okay. So first option we have choose to the for the first replacement of yes we have choose the first option. For second, third, and fourth. Finally, for everything for till third, fourth replacement, you have used the first alternative. So finally, you have got the required string, but you are having an extra yes. So that s could be replaced with an epsilon here. So in this way, you can derive it. Next, we can go with the third example. That is, you have to construct a CFG for L equal to 0 power m, 1 power n. So, where m is greater than n. So, based upon this, what are all the languages you can generate? So, there could be an assumptions that L could be, so initially when m and n are equal, so it can be either equal or m should be greater than n. So the number of zeros should be either equal to the number of ones or it can be greater than number of the number of zeros could be greater than ones number of ones. So here first assumption could be 0 1. So it can be 0 also. So why I'm going with 0 is, so the number of zeros that is could be greater than 1. So in such cases, the 0 could be there, 1 cannot be also there. So here the given the criteria is m should be greater than or equal to 1. And that they didn't give any condition like m should be m could start with 0 or n could start with 0 and so on. So based on these assumptions, we can make our own predictions. So 0. Next, you can also have 0 1. So since number of zeros and ones can also be equal. Next, double zero one, triple zero double one, double zero one. So double zero four zeros triple one. So in all these strings, you are having the number of zeros is greater than or equal to the number of ones. So based on this, we can write down the productions. So G, so what could be the productions? Here you're using two non-terminals here, S and A. So here, yes, S tends to 0, S1 or the second alternative can also be A. So again, the S, A is again, again a production rule is written for A equal to 0A or epsilon. So based on this production, how will you interpret this string 5 zeros with triple one? So this automatically is a string of the, it belongs to the language. So let us derive this. So initially we can start with yes. So yes is the starting non-terminal here. So here what could be written here? 0 for number of zeros is 5 and number of 1 is 3 here. So based on that, I'll go with the first alternative 0 S1. 0 S1. So now you have to replace S here. So here, so again you can go with 0 S1. 0 yes 0 0 yes 1 1. So now in this step you have got the required number of ones. Sorry, one more it is there. So again s can be replaced with 0 s1. So in this step you have got number of ones as like the required string. So now we have to replace s with more number of zeros. So one number of ones is sufficient here. So as a result, for this you can use the second alternative, that is 000. So instead of yes, you can replace with a, and you can go with 111 here. Now a is a non-terminal which you have to replace it. So for this a, we can replace with 0a. So 0a 111. Now again one more 0 has to be derived here. So 5 zeros. Again a can be replaced with 0a 0A, triple one. So now the required string is 5 zeros and triple ones, but we have already got it. Now A is an extra non-terminal here. So now A can be replaced with its best option here. So here you can go with A can be replaced with either 0A or epsilon. So now automatically, now at this point we have reached our required string. So you can replace A with epsilon here. So automatically you have got the required string. Next, we can go with the example 4. That is, we are going to construct a CFG, that is a context-free grammar for simple expressions. So for the simple expressions here, we are considering only two operations here, plus and asterisk symbol, that is addition and multiplication. So the expression can be represented with a single non-terminal E, and F can, that is a single non-terminal, and the expression can also be either the expression can be an alphabets or it can be zeros and ones. So for our convenience, we are insisting that we are having only two alphabets A and B. So it can be from small a to small z, any values. But here, for example, we are taking, for our convenience, we are taking A and B. So for numbers, we are taking 0, 1, 1 automatically. So here addition and subtraction alone we are considering here, and when there is an expression, so here you can have open bracket and close bracket. Okay, so now for this we have to write down the productions. So here having two productions here, two production rules here. E tends to, it can be addition E plus E, or E star E, or it can be within the brackets, within the parenthesis. Next it's F. So what is F here? So F could be, it can be either 0, 1, or it can be 0 plus 1, or it's so on. So automatically, so here F can be further expanded with, initially it can be 0, it can be 1, or it can be A, simply A, or it can be simply B, or it can be AF, BF, 0F, 1F, and so on. So this could also be an expression. So these are all the various way of replacing the non-terminals. So let us go with the left and rightmost derivation for this example. So let us consider a simple expression like A star A bracket AB plus 10. So this could also be an expression. So before that we have to know what is leftmost and rightmost derivation. The leftmost derivation is nothing but you will be performing the substitutions starting from the leftmost non-terminal. That is, you will be replacing the leftmost non-terminal first, and then you will be directed towards the right side of the productions. Whereas the right side, the rightmost derivation is nothing but you will be performing the substitutions of the non-terminals from the rightmost till the towards the left. So now let us take the example A star AB plus 10. So this could be how it could be derived by using leftmost derivation and rightmost derivation. So initially the expression can be a simple E. So E is a starting non-terminal. So you have taken E. So E can be here. So automatically A star AB plus 10. So automatically here there are left side operand is A and the right side of the operand is AB plus 10 included within a bracket. So we can go with E star E. Next. So E can be further expanded with F. So based on the derived, based on the yield what is here, so based on that you have to perform you have to do the substitutions perfectly, and you have to choose the alternatives as such. So here E can be replaced with F, again F. So now what you have to do is, so here A star is there. So what is next here? A into F. Next again A. So F can be replaced with epsilon because A star is required. So you can replace F with epsilon here. Next A into E. So the left side operand you have got it. Next you have to go with the move on with the right side of the operand. So right side of the right side non-terminal is here capital E. So here what is the right side of the operand here? EB plus 10 enclosed within a bracket. So automatically the E can be replaced with bracket E bracket. Again, so it is plus operation. So here E can be again replaced with E plus E in the very next step. So here it is AB. So if it is AB, then you have to replace E with F here. So F can be further replaced with AF, Again, f can be replaced with bf. In the next step, the f can be replaced with epsilon. So finally, you'll be getting ab plus e here. Again, in here, you're having 1, 0. So for 1, 0, again the z could be replaced with f here. Next, f could be replaced with 1f. Next, 1, 0, f can be replaced with 0f. Again, you have got it 1, 0. Again, finally, the f could be replaced with epsilon. So finally, you have got the required yield. So here leftmost direction. So right from the starting of the derivation till the end of the derivation, the leftmost derivation is first, the leftmost non-terminal is first replaced and following it with the following on towards the right side substitutions. Whereas in the right side of the in the rightmost derivation, so you can just see the app just opposite of the LMT. So here on the right side of the derivation, so you go with e plus e into e. Next, so here the second operand should be first replaced and you have to get the required yield. Then you have to replace the left side operand, that is the first operand. So first you have to replace, same process has to be repeated but in somewhat in a reverse manner. So the first thing, the second operand must be the rightmost non-terminal has to be replaced. Then next to its immediate left, the leftmost non-terminal has to be replaced and its leftmost non-terminal. So similarly its end. So see here, second operand e is replaced with e enclosed with brackets. Next, e can be further replaced with e plus e. Next, e can be replaced with f. So e can be replaced with, so f can be replaced with 1f. Next, 10 f, 10. Next, so after did with 10, we have to get the string AB here. So the second, its immediate left non-terminal is being performed with the same as like transformations, and finally you'll be getting AB plus 10. Then the final left out is the first operand, that is E. So similarly you have to perform the same transformations and finally you will be getting A into EB plus 10. So this way the rightmost derivation has to be done. Next we can go with the example 5, that is how a grammar has to be constructed for a palindrome. So what is a palindrome? A palindrome is one string where where the particular string, when it is being reversed, it should also get the same string. So for example, A, B, B, A, when it is being reversed, we will be getting the same A, B, B, A. So the string on reversal should have the same word. There should not be any changes. So an input string belongs to this language if and if it will be generated by the context-free grammar. For example, take, so here we are going with zeros and ones here. So let the terminal symbols be zeros and ones. So here W equal to the string is 0 triple 1 0. So when it is being reversed, you will be getting the same string A 0 triple 1 0. So for this you have to write down the required productions. So here you can go with a starting non-terminal A. So A, for this you can choose many of the alternatives 0A 0. So the language what could be generated here is L equal to, it could be immediately 0, oh sorry, it could be either 0, it could be either 1, okay, it could be either 1 1, it could be either 0 0, it could be 0 1 1 0 0, 1 1 double 0 1, 0 triple 1 0, and so on. So these are the languages you can generate it. So now for this, the productions can be as such. A tends to 0A0. So based upon the language what you have generated, so based on that you have to write on the right side of the productions. So 0A0, it can be 1A1, 0, 1 or epsilon. So this is the grammar for the palindrome. So let us derive W equal to 0 triple 1 0 by using this grammar. Okay. So it is 0 triple 1 0. So initially, so you'll be starting with starting non-terminal A. So A can be replaced with 0 A 0. Next, now A is the non-terminal that has to be replaced here. 0 1 A 1. So A can be replaced with 1 A 1 0. Next, so next what is the finally left one is center 1. So here I'll go with 0 1. Now A can choose the or A can be replaced with one more 1 here 1 0. So now the required string is generated by the given grammar. So I hope you have understood about the context free grammars in this video. Thank you.